Hello all, welcome again. This is a series of STM32H7 tutorials. We will step into system core, and today's our topic is onto the reset and clock control. In this session we'll go through the overview of RCC and reset key features, reset sources and reset coverage, hold boot function, clock key features, high speed internal clock, that is HSI, and low speed internal clock, that is CSI, and HSC, that is high speed external clock, HSC, LSI, low speed internal clock, LSE, that is low speed external clock, PLLs, and simplified clock distribution, simplified clock tree, simplified peripheral clock distribution, peripheral allocation, system states and autonomous modes, kernel clock requests, peripheral clock gating, interrupts and related peripherals. So please subscribe to our channel if you did not subscribe by clicking subscribe button and press bell icon for your personal notifications. So STM32H7 reset and clock control manages the reset, the system and peripheral clocks generation. The STM32H7 X3 or X5 or X7 devices embed 4 internal oscillators, 2 oscillators for external crystal or resonator and 3 PLLs, phase lock loops. Many peripherals have their own clock independent of the system clock. The STM32H7 or RCC provides high flexible in choice of clock sources, which allows the system designer to meet both power consumption and accuracy requirements. The numerous independent peripheral clocks allow a designer to adjust the system power consumption without impacting the communication baud rates, and also to keep certain peripherals active in low power mode. So safe and flexible reset management without any need for external component reduces the application costs. The RCC manages several types of resets: the power reset, the system reset, D1 and D2 domain reset, the local resets and the backup domain reset. Let's have a quick look at reset sources. So thanks to the voltage monitoring function included in power block, the filters embedded in the NRST pad and the RCC reset control, the amount of external components is reduced to a single external capacitor connected to the NRST pin. The first type of reset is the system reset, which resets all the registers except certain registers for the reset and clock control and power controller. It also does not reset the backup domain. Here you can see, right, the block diagram. Have a quick look at it. Many sources can generate a system reset and valid voltage on VDD or VCore supply. See power block for details. An invalid voltage on VDD due to the brownout function. The brownout function allows the user to choose its own threshold levels for the VDD supply. See power block for details. An exit from standby mode, a low level on the NRST pad, a timeout from one of the important watchdogs, IWDG 2:1, and a timeout from one of the window watchdogs if allowed by the reset scope bits, WW2:1 RSC, and software reset request initiated by the Cortex M7 named CPU1 or Cortex M4 named CPU2. A low power mode security reset which is generated when stop or standby mode is entered, but it is prohibited by the option byte configuration. You should note as well that the system reset asserts the NRST pad, which can be used to reset external components on the board. The reset source flags can be found in the RCC control and status register. The power on reset is generated when the VDD or Vcore voltages are lower than a certain voltage threshold. Let's have a quick look at the reset sources now. So backup domain of the reset occurs when the BRDST bit in the RCC underscore BDCR register is set to 1 by application as shown in this figure. When the VDD and VBAT are powered on, if both supplies have previously been powered off, a D1 or D2 domain reset occurs when one of the two domains has been switched off. In addition, the peripherals have individual reset control bits. It is also possible to reset the CPU1 and its associated watchdog window WWDG1 RST underscore C1, and to reset the CPU2 and its associated you have WWDG2 RST underscore C2. So the power on reset is the reset having the largest coverage. So the power on reset results all the logic located in the VDD and Vcore domains except those in the backup domain powered by the VBAT, which contains the RTC and the external low speed oscillator. Note that the power on reset also triggers the system reset. So the NRST pad is asserted during a power on reset. The system reset resets most of the logic located in the VDD and Vcore domains except certain resources located in the RCC and PWR, that is power blocks. The backup domain is not affected by this reset. The backup domain resets the backup and the backup domain powered by the VBAT, which contains the RTC and external low speed oscillator. The domain resets the complete D1 and D2 domains when the corresponding power switch is activated. So there is something called as hold boot function, which can be used to set one of the two processors to hold after a system reset or an exit from standby mode. This function can be useful if one processor has to boot in advance for example, to perform the system initialization. Note that when one of the processors is in hold, it does not prevent the system from entering standby mode. Some of the clock key features are offered by the RCC, which can be selected depending on the low power, accuracy and performance requirement. STM32H7, X3 or X5 or X7 devices embeds 4 internal RC oscillators. They are a high-speed internal RC oscillator HSI, which can work at 64, 32, 16 or 8 MHz. Low power internal RC oscillator, that is CSI, working at 4 MHz. An accurate RC oscillator working at 4 MHz. A low speed internal 32 kHz RC oscillator as LSI. So STM32H7, X3 or X5 or X7 devices embed 2 oscillators for use with external crystal or resonator. A high-speed external 4 to 48 MHz oscillator HSC with a clock security system, and a low-speed external 32.768 kHz oscillator LSC also with the clock system security. Device also embeds three-phase lock loops, that is PLLs, each with 3 independent outputs for clocking different peripherals at different frequencies. Let's look at HSI first. HSI is a 64 MHz RC oscillator, which provides the fast wake-up times. The HSI is trimmed during production testing and can also be used trimmed. It can also be the user trimmed. A dedicated divider can generate a 32, 16 or 8 MHz clock. The HSI can be selected as a clock at wake up from system stop and as the backup clock if an HSI failure is detected by the clock security system. The HSI can remain powered when the system goes to stop mode in order to speed up the wake up time. Certain peripherals such as I2C or an UART or USART or LPUART can request the activation of the HSI in system stop mode in order to generate wake up events. The HSI is enabled by peripheral only for wake up sequence detection and remains disabled outside of this wake up sequence. Whereas LSI is there is low power internal clock or CSI. CSI is a 4 MHz RC oscillator which provides fast wake up times. The CSI is trimmed during production testing and also can be user trimmed. The CSI can be selected as a clock at wake up from system stop. The CSI can remain powered when the system goes to stop mode in order to speed up the wake up times. Certain peripherals such as once again here is I2C and USART, LPUART can request the activation of CSI in the system stop mode in order to generate wake up events. The CSI is enabled by the peripheral only for the wake up sequence detection and remains disabled outside of this wake up sequence. HSC clock, the high speed external clock, provides a safe crystal oscillator system. The HSC supports a 4 to 48 MHz external crystal or ceramic resonator and also an external source in bypass mode. A clock security system automatically detects an HSC failure. When dedicated, a non-maskable interrupt is generated and a break input can be sent to timers in order to put critical applications such as motor control in a safe state. When HSC failure is detected, the system clock is automatically switched to HSI, so the application software does not stop in case of a crystal oscillator failure. When it comes to the LSI, STM32H7 devices, that is X3, X5, X7 devices, embed an ultra low power 32 kHz RC oscillator LSI, which is available in all modes except VBAT mode. The LSI can be used to clock the RTC, LPUARTs, the low power timers and the independent watchdogs. The accuracy of LSI is plus or minus 1.8%. The LSI consumption is typically 132 nanoamps. So LSI 32 LSC, that is low speed external clock, 32.7 kilohertz low speed external oscillator can be used with external quads or resonator or with an external clock source in bypass mode. The oscillator driving capability is programmable. 4 modes are available from ultra low power mode with a consumption of only 290 nanoamps to high driving mode. A clock security system monitors the failure of the LSC oscillator. In case of failure, the application can switch from the RTC clock to the LSI clock. The clock security system is functional in all modes except VBAT mode. It is also functional under reset. The LSE can be used to clock the RTC, the USARTs or low power UART peripherals and the low power timers. So whereas we have phased lock loops, we'll get onto that. PLLs, in short we can say, embedded in STM32H7 devices provide a flexible way to generate the required frequency for the system or peripheral clocks. They offer a wide input frequency range from 1 to 16 MHz. If the input frequency is between 1 and 2 MHz, then the user has to select the VCOL. path. If the input frequency is between 2 and 16 MHz, then the user has to select the VCOH path. The two VCOs also have a smart frequency ranges from 150 to 420 MHz for VCOL and 192 to 836 MHz for VCOH. The PLLs also provide three different outputs which all are derived from the VCO output via post dividers DIVP, DIVQ and DIVR. In addition, it is possible to change the values of the post divider without disabling the PLLs. The application just needs to disable the corresponding post divider, change the division ratio and re-enable the post divider. In order to get a duty cycle close to 50%, the application has to program the post dividers to even values. In addition, the PLLs can be switched to fractional mode, allowing a high precision in the VCO frequency. The 13-bit fractional divider can be changed without disabling the PLLs. This feature can be used to perform accurate clock drift compensation. We'll look into the simplified clock distribution in a while. Please make a note of it. So I need to say like PLLs share the same clock source, HSI, CSI or HSC. Each PLL has a dedicated pre-divider in order to adjust the reference clock for PLL. PLL2 and PLL3 are dedicated to the generation of kernel clock for the peripherals. Certain peripherals such as SAI, USB, etc. may require a specific frequency. The PLL1 P output is used as a system clock for processors and buses. PLL1R is dedicated for the debug trace, and PLL1Q is also used as kernel clock for peripherals. Note that the PLL's clock source cannot be changed if one of the PLL is enabled. Let's have a look at a simplified clock tree. After this, the simplified clock can be derived from the HSI, CSI, HSC or the output of DIVP of PLL1. Here you can see in this tree, the switch used to select the system clock is dynamic, meaning that it is possible to change the frequency on the fly without generating timing violations. In addition, all the prescalers presented in the figure are dynamic, so they can be changed on the fly as well. It's marked in red, making the frequency scaling operation very simple. The clock of the CPU1 does not exceed 480 MHz. The AHB clocks do not exceed 240 MHz, as well as the CPU2 speed. The APP clocks do not exceed 120 MHz. Note that HRTIM, high resolution timer, and certain timers can use clock frequencies up to 480 MHz. The clock for RTC or AWU can be selected from among LSC, LSI or HSC divided. Note that when HSC divided is used as a kernel clock for the RTC or AWU, the frequency cannot exceed 1 MHz. Note as well that if LSI is used as a kernel clock for RTC or AWU, the RTC or AW will no longer be clocked if the VDD and vCore supply are removed. If HSC is divided used as a kernel clock for RTC or AWU, the RTC will no longer be clocked if the system goes to stop mode or if the vCore supply is removed. The LSC can remain enabled in all low power modes and in VBAT mode. The RCC also provides two clock outputs signals, MCO1 and MCO2. A prescaler allows the application to adopt the frequency to the pad's capability. Okay. So many STM32H7 peripherals have different clocks for data control stream via the processor bus interface as well as the clock for the specific peripheral interface. Generally, the clocks for the data and the control streams via the processor bus interface are named bus clock or bus clocks. The clocks for the peripheral specific interface are named kernel clocks. The peripheral clock represents the clocks received by the peripheral. Bus clocks and the kernel clocks. Having a separate bus clock and kernel clock allows the application to change the interconnect and processor working frequency without affecting the peripheral. For certain peripherals, it is also possible to disable the bus clock as well, as long as the peripheral does not need to transfer data to the system. So it gives a good flexibility on the frequency selection for the bus processor and memories and the real need of the peripheral interface. For example, UARTs have a kernel clock which is used among other things by the baud rate generator for the serial interface communication and APB clock for the register interface. In addition, certain peripherals are able to request this kernel clock when they detect specific events. The distribution of the clock is not detailed in this presentation. Please refer to the reference manual for specific detail. Most of the peripherals receiving a kernel clock have a dynamic clock switch to select optimal clock source. The proposed clock sources generally come from one of the 7 PLL outputs dedicated to the kernel clock generation, internal or external. This is mandatory for peripherals needing a kernel clock when the system is in stop mode. Pads, for example, on peripherals using an external PHY, but also for audio as well. In order to use a clock reference from an external device, other internal peripherals for synchronization between the blocks, the dynamic switching facilitates the transition from one source to another. The RCC registers are also used to configure the kernel clocks for all peripherals. So that leads to a point like gating, right? Peripherals generally receive one or several bus clocks, one or several kernel clocks. Each processor can control the clock gating of the peripheral clocks via dedicated registers located in the RCC. The gating of peripheral clocks depends on several parameters. The clock enable bits, each processor have a dedicated control bit for that named C1 underscore PERX enable EN and C2 underscore same for simplification. The low power clock enable bits, the processor states, that is C run, C sleep or C stop. Finally, the autonomous bits for peripherals located in D3 domain setting in the bit C1 underscore PERX enabled to 1 indicates that the peripheral PERX is enabled for the CPU1 and setting the bit C2 underscore PERX EN to 1 indicates that the peripheral PERX is enabled for the CPU2. This operation is named allocating a peripheral. It is important to note that the RCC offers 2 registers allowing each processor to enable or allocate peripherals. The peripheral allocation informs the RCC that CPU1 or CPU2 enabled a peripheral. This information is used by the RCC for the clock control in LPMs, that is low power modes. So before using a peripheral, the CPU have to allocate it. The same peripheral can be allocated by both processors. It is up to the application to avoid resource conflicts. Okay, you can see a typical allocation here. Certain peripherals are implicitly allocated to a specific processor, the flash, access RAM, ITCM, DTCM1, DTCM2, 20 are implicitly allocated, that is enabled for to CPU1. The CPU2 can allocate any of them, but by default they are not allocated to CPU2. When the D2S RAM1, D2S RAM2 and D2S RAM3 are implicitly allocated for CPU2, the CPU1 can allocate any of them, but by default they are not allocated to CPU1. Certain other peripherals are allocated to both processors. This is the case for IWDG1, IWDG2, RCC, PWR, EXTI and D3 SRAM. When a CPU allocates a peripheral, this peripheral is linked to the processor state for the low power modes. The CPU plus the peripherals allocated by this CPU and the associated interconnect is considered by the RCC as a CPU subsystem. The D1 and D2 domain core voltages can be switched off. To give a simple example of how the RCC use the peripheral allocation, we can state that the RCC will not allow a domain to be switched off if one of the peripherals of this domain is used by the processor of the other domain which is not switched off. So let's look at the following table, which gives a simplified view of the system states versus domain states. A domain is in DRun mode when its bus matrix is clocked. Its bus matrix will be clocked if a CPU which is in CRun or CSleep mode allocates a peripheral on this domain. A domain is in DStop mode when its bus matrix is no longer clocked. The CPU of this domain is in CStop mode. The other CPU is not allocating peripherals on this domain, or the CPU is also in CStop mode. A domain is in D standby mode when its vCore supply is switched off. Note that it is possible to keep only the D3 domain in DRun mode while other domains are in D standby mode. So note that the system restarts, for example, after a system reset, the HSI is selected as the system and the clock peripherals. The CSI, HSI and HSC are off, as well as the PLLs. The LSI is still working if it was the previously enabled. After system stop, the PLLs are switched off. The application can choose either the HSI or CSI as the system clock and peripheral clock. HSI and HSC are off after D1 or D2 domain exits D-stop or C-stop mode. The RCC maintains the same clock setting as the one used before going to the low power modes. There is something called as autonomous modes, offers the possibility to provide the peripheral clocks to peripherals located in D3 even if the CPU to which they are allocated is C-stop mode. If both D1 and D2 domains are in D-stop or D-standby mode, the gating of the clocks of the peripherals in the autonomous mode depends on the mode of D3 domain. If D3 domain is in DRun mode, the peripheral will receive its peripheral clocks. If D3 is in D-stop mode, the peripheral clocks are gated, but the peripherals can still request the kernel clock if they have this capability. The autonomous mode does not prevent the D3 domain from entering D-stop or D-standby mode. The D3 domain is able to switch alternatively from DRun or D-stop mode and then from D-stop to DRun mode according to the peripheral activity. For example, if the system is expecting messages via I2C, the complete system can be put in stop mode. When the I2C detects a start bit, then it will generate kernel clock request. The request enables the HSI or CSI and a kernel clock is provided only to the requester. then the I2C can decode the incoming messages. Several cases may occur in that if the device address of the incoming message does not match, then the I2C releases its kernel clock request until a new start condition is detected. If the device address of the incoming message matches, the message has to be stored in the D3 local memory, and I2C is enabled to generate a wake-up event on address match in order to switch the D3 domain to DRun mode. When the D3 domain is in DRun mode, the bus interface clock is activated, allowing the I2C to transfer the message into the memory via DMA1. If the D3 local memory is not full, then the D3 domain will go back to the D-stop mode without any CPU activation. If D3 local memory is full, the DMA1 can generate a wake-up event in order to activate CPU1 or CPU2. So certain peripherals such as UART and I2C are able to asynchronously detect events requesting a kernel clock for the processing. The RCC can provide on demand a kernel clock to those peripherals when the CPU allocating the peripherals is in C-stop mode or if the system is in stop mode. The kernel clock request will work if the selected kernel clock is HSI or CSI in order to speed up the activation time. The HSI or CSI can be maintained activated during system stop mode. In system stop mode, the LSI and LSC clocks are still available for peripherals. So, a kernel clock is provided to the peripherals allocated in D1 or D2 domains if one of the following conditions is met. When the CPU to which the peripheral is allocated is in CRun mode and if its enable bit is set to 1. When the CPU to which the peripheral is allocated in C-sleep mode and if its LP enable bit is set to 1. When the CPU to which the peripheral is allocated in C-stop mode and if its LP enable bit is set to 1 and the peripheral is generating a kernel clock request and the kernel clock source is HSI or CSI. When the CPU to which the peripheral is allocated is in C-stop mode and if its LP enable bit is set to 1 and the kernel clock source of the peripheral is LSC or LSI. The bus interface clock will be provided to the peripheral only when conditions 1 or 2 are met. A kernel clock provided to the peripheral PRX of the domain D3 if one of the following conditions is met. Right, when the CPU to which the peripheral is allocated in CRun mode and if its enable bit is set to 1. When the CPU to which the peripheral is allocated in C-sleep mode and PRX LPEN equals to 1. When the CPU to which peripheral is allocated in C-stop mode and the D3 domain is in DRun and if its LP enable bit is set to 1. When the CPU to which the peripheral clock is allocated is in C-stop mode and D3 domain is in D-stop and if its LP enable bit is set to 1 and the peripheral is generating a kernel clock request and the kernel clock source is HSI or CSI. When the CPU to which the peripheral is allocated is in C-stop mode and the D3 domain is in D-stop mode and if its LP enable bit is set to 1 and the kernel clock source of the peripheral is LSC or LSI. The bus interface clock will be provided into peripherals only when the conditions 1, 2 or 3 are met. All the first 3 conditions. So have a quick look at interrupts, events and their description here. This slide list the RCC interrupts, the LSC and HSC clock security systems, the PLL ready, and all 6 oscillator ready signals can generate in an interrupt. Have a quick look at it. And related peripherals for this is STM32H7 power control PWR and asynchronous interrupts and the event controller EXTI. I hope you like this video. If you like the video, please click like button. If you did not subscribe, please subscribe to our button and stay tuned for more onto the system configurations. Next would be the NVIC, I believe, interrupt controller. Thank you again.